Okay, everyone. Back, and I'll get through this as quickly as I can. We can go to lunch. Python, and also a little bit about how to use gem5. So you ran a couple simulations with gem5, hopefully. Now I want to give you a brief introduction to developing with gem5, and we'll cover a lot more on Wednesday and Thursday on this. So I want to talk a little bit about why we want to develop gem5, getting gem5 so you can develop with it, and talk about gem5's architecture. So that's going to be some of the questions about sim. And then briefly talk about some coding. Okay, so why might you want to develop with gem5? Why might you want to, and when I say develop, I mean modifying gem5's code. Yeah. Yeah, because you want to do something that's not there. More specifically, or other reasons why? For those of you that used gem5 before, I imagine you modified the source. You usually do. Why?
We need to change the replay logic when to issue instructions.
Okay. Yeah, so you're changing the logic of a module. So some component, you wanted to change the architectural design. So you had to change the logic. Why might you want to develop with gem5? Yeah, so adding new statistics to learn. Do research. Add new models. Yeah, you want to come up with an idea, add a model for it. And so to add a new model for a new idea, you're 5. Without changing the source, you could do some things. You can vary parameters, you can set up different systems, but you can't really evaluate novel architecture ideas. Maybe a few, but not anything super interesting. One other reason why you want to develop with gem5 is that there's a bug somewhere, and you want to fix it. And then hopefully contribute it back. Everybody else in this room and across the gem5 community will all not have to run into that same bug that you ran into. So that's the reason. 5, we need to download it and build it. So in the code spaces we've already closed. I would encourage you to now execute this last line. So cd to the gem5 directory, and then let's build gem5. For the number of threads, I would use 17. So build /x86/gem5.opt minus j17. So we'll see that command. So cloning gem5. If you want to learn more about Git, the Git book here is a really good resource. We use Google source as the main, not GitHub, although most 15 minutes out of date. But Google source is where it lives. If you want to contribute back, you have to clone from Google source, not GitHub. We have 2 branches in gem5, stable, which is the default branch. This is updated really once every few months, although for bug fixes or minor releases, it'll be updated. And then we also have develop. Develop is updated quite frequently, often multiple times a day. Develop will be updated. So if you're using gem5 for research, I would encourage you to start with stable and use stable. On develop that you know you need for your research. Okay, so back to the gem5. So we use, but different and harder to use. but it has a lot more features. No, okay. So you can be very, it gives you a lot of flexibility how the build system works. In some sorry. One of my least favorite, maybe something we will replace. I really want to replace it with Bazel, which is yet another complex build. Anyway. So set of parameters gods. The file script interprets build is the direction we're going to put in. x86 is the defaults we're going to use for the build. If you look at the file build op/x86, it has some defaults in it. So that's where the defaults come from. And then the .opt is also a parameter. Build gem5. We want to .opt says we want to build it with compiler optimizations on, but also with debug flags. You could build .fast, which has compiler optimizations and no debugging, which is smaller and faster. But if something goes wrong, it's hard to debug. Or you can build it in .debug form, which does not have any compiler optimizations. So if you need to use GDB and some variables optimized out, then you can go back and recompile .debug. Any questions on this, other than why scons? Okay. I'm going to give you some really bad news and tell you this might be changing in the next release or two. Changes on gem5's code review to change this. They haven't been accepted yet. We'll see what happens. Okay, so now I want to talk briefly about gem5's software architecture. So gem5 consists of many sim objects. These are the models. So anything that you want to include in the system is a objects in gem5 inherit from class sim object. Not are sim objects. You can see a list of a few from A to B on the right. So like the non-volatile memory model, the base indexing policy, the branch prediction unit are all sim objects. These represent some physical component in the system. So a sim object is a model, and it's implemented in plus, and you find it in the source directory. When you create a model, you might want to create some parameters for that model. Say if it's a cache, maybe it has a size, associativity. Those are for your model, also source, but you what we're going to call a sim object declaration file. So this is a Python file that declares the sim object and the parameters. And this is the binding between Python and us. My R on Wednesday morning will show you how to write. Which are the models, which correspond to models in C++. Instances in Python specify some parameters. It's a little complex and weird, extremely flexible, and very powerful. Okay. So I want to try to talk a bit about model versus parameter. So on the right, we have a picture of an out-of-order core stolen from Wikichip, which if you haven't seen wikichip.org, it's a great resource for details about current microprocessors. So this is a Sunny Cove, which I think is one of the more recent Intel microarchitectures. And so this would be some model that you could write in C++. So this model might have a scheduler. It might have a rename, a reorder buffer. It might have an allocation queue. Then you might have some parameters to your model. For instance, how many micro-ops can be issued from the issue queue to the reorder buffer per cycle. In this particular instance, it's 6. But you can imagine that be a parameter to your model. You might also have a parameter to your model saying which branch predictor to use. Might be another sim object that you could plug into this. You know, you might have parameters with how many cycles it takes for an integer operation. So you have this model which can take parameters. And these parameters are the parameters that you allow for your model are going to be specified in Python, and then you also set up which values to use in the Python run script. Questions on the difference between a model and a parameter and a generic model versus an instance? Okay. So more nomenclature today. So we can extend a model to model new things. So we can extend the base CPU to model an outer CPU. Or extend a cache to be a special kind of cache. Or maybe in Python, we can specialize a model with specific parameters. So in Python, you'll often see, so for instance, class i7 CPU would inherit from O3 CPU, and then you'd specify, I want the issue width to be 10. Because if you look at this, I'm pretty sure that that's 10 for the issue width. So you have a model, which is in C++, and then we can specialize that model with specific parameters in Python. And so this afternoon, Bobby will be going through the standard library and a lot of examples of specializing C++ models in the standard library. Any questions on this? Okay. Okay, so let's talk about the way simulation works in gem5. So gem5 is a discrete event simulator. So you have events that are simulated with discrete time, not continuous time. So we have an event queue, and every event in the event queue is some function that's going to execute, and it has some time that it needs to execute. So for instance, here we're about to execute an event at time 10. So what happens is gem5 runs in a loop, and that event loop, or the simulation, the sorted list of the youngest, grabs the event with the list to execute. It then executes that event, which is calling some function. And then that event might create new events. For instance, in this case, the event at time 10 created an event at time 55. That then goes back onto the event queue. And then we just do this over and over again. Event number 11, that could create an event. Say it creates an event at time 51. Well, this event queue is a priority queue. It's a sorted list. So then that would go into wherever it needs to go. So it's executed in order, in time order. So when you're creating cycle level simulation, you will schedule events to happen at particular cycles. Or you could even schedule events not at cycles, but so if you have clock domain crossings, you can deal with clock domain crossings by scheduling an event at the right time. These kinds of things. So events are always scheduled at a particular time. Time always goes forward. So you can schedule an event at any time in the future. You cannot schedule events at times in the past because causality would be broken.
You can be like round robin schedule.
So you schedule, so there isn't any priority or anything. Events are scheduled for a particular time. So I say I want, so I'll give you an example in a second. It's a good question. Any other questions on this? Okay, so all sim objects can enqueue events. One thing being a sim object is you can enqueue events. And we'll cover this a lot more on Wednesday. So let me give you an example, which I think will answer your question. So CPU, or simulating a system. So we're going to have an event, which is fetch the first instruction. This function, which sends a request to the cache. When that request comes to the cache says, oh, it's going to take me, I don't know, some amount of tag latency, say 2 cycles, to check the tag. So it schedules an event for 2 cycles in the future. So then the event is eventually executed. So it looks at the request and says, oh, that is a tag miss. So I'm going to miss in the L1, and I need to send this to DRAM. So it calls a function on DRAM, and maybe that takes some amount of time to get there. So it's going to schedule an event to happen with the interconnect latency for the future. And then at that time, we're going to check a DRAM. So then at that time, queue, and then maybe it needs to sit in that queue for a little while. Maybe it's the only thing in the queue, so it gets popped off the queue. And then we can schedule another event in the future of however long it takes to read DRAM. So maybe it takes 10 nanoseconds. The page was already open. So then 10 nanoseconds later, we get the data out of DRAM. Remember, this is an execute and execute simulation. So we don't get the data until the time we would actually get the data. We schedule an event for the future, which is the response latency, however long it takes to get back. And then at that time, we receive the data in the cache. Then the cache forwards that data to the processor, which say decodes the instruction, and maybe at the same time, it executes the instruction. And then at some time in the future, it says, OK, the instruction is going to be ready to write back. And then schedule another event for the future, which will fetch the next instruction. So this is somewhat like the timing simple CPU works, which I think we'll hear more about tomorrow morning. Pretty sure we'll hear more about tomorrow morning. Yeah?
For example, if we miss in the cache and if we schedule an event for a read in the RAM, if there is another event that takes a shorter time but that doesn't depend on this, will not get executed.
Events will only be executed at existing. And all the events scheduled for that will be executed in that exact same tick. So there's some global idea of time, and we look to see what the next event is. We fast forward time to that next time, execute all those events. Then we fast forward time to the next time, execute. Yeah?
Is there a situation where happen where like two different sim objects want to schedule a particular event at the same time?
Yeah, so multiple events can be scheduled at the same time. They are executed in arbitrary order, modulo a couple special cases. You shouldn't depend on an event happening in the same tick. You can get some circular dependencies that break things. Any other questions? OK, so this is how gem5 works. We have sim objects, and queue events. The end. You have now learned everything about gem5. All right, so a bit about discrete event simulation. So this time is a unit. So we call this in gem5 simulation rate, which by default is a tick is equivalent to 1 picosecond, or there are 10 to the 12 ticks per second. So this is the simulated time. Not the simulator time, the simulated time. is operating at at the granularity of 1 picosecond. So like the quantum is 1 picosecond. Okay, any questions about simulator, discrete event simulation, et cetera? Only one more slide between you and lunch. Okay, so last thing, as we go through, to keep in mind is try to be a good software engineer. Because so much of my communication with so being a software engineer is all about communicating with your future self. Your future self will hate past you if you didn't write good code. Gem5 has a coding style. I would encourage you to take a look at it. You don't have to read the whole thing. Most importantly, try to match the style of the code around you. It just makes it so much easier to read. Just like writing a paper, when you write a paper, you should write it in the way that the reader expects to read it. When you're writing code, you should write it in a way that some future code reader expects to read it. I would suggest using branches. Use Git. Git's really nice. We don't use branches in Gem5 mainline development, but locally, all of us use tons of branches. We'll talk about how to do Gem5 development on Friday. Messages. I can figure out why you did that thing. And this link down here. Change requests is really useful. Okay, so that's all I have. We have lunch here in a minute. A couple of quick administrative things. First, which you may or may not be very excited about. I won't be talking for a while. You won't hear from me again until like Thursday. So everybody else will be doing a lot of talking.